Good morning, one and all. Today, I'm going to discuss non-deterministic finite state automata, or simply NFA, non-deterministic finite automata. Unlike deterministic finite state automaton, in non-deterministic finite automaton, you can have more than one outgoing transition for the same input symbol. For example, suppose that you have, say, Q0, Q1, Q2. Suppose that you have a that is 0 or 1 followed by 1 0. Suppose that this is a finite automaton. Here, for the same input symbol 1, from Q0 can either stay in the same state or it can switch to Q1. That means for the same input symbol it can have more than one transitions. But in deterministic finite automaton, for the same input symbol you can have at most one outgoing transition. But here in this case you can have more than one outgoing transition for the same input symbol. See how this is accepting a string. For example, this is a language acceptor and this is accepting all strings which is ending with 10. All strings ending with 10, this will accept. See how that is done. For example, initially suppose that you have the input symbol 0 1 1 0. 0 1 1 0. Suppose that initially the finite control is in state Q0, and Q0 upon reading 0, what will happen? Q0, that is unique, that means Q0 upon reading 0 is staying in the same state, that means Q0 on accepting 0, it is staying in the same state Q0. Okay. Now, for the second input symbol 1, what will happen? Now the finite control is in state Q0, and upon reading the next one, what will happen? It can either stay in the same state or it can switch to a new state. That means now you are splitting your finite control. Now you have two finite controls. You have split your finite control into two, and one finite control is going this path and other is staying in the same state. That means upon reading one of the finite controls is staying in the same state Q0, and the other finite control, what will happen? That is switching to the state Q1. Now you have two finite controls. One is in state Q0 and the other is in state Q1. Okay. See, after that the two finite controls are advancing to the next input symbol, and the next input symbol is 1. What will happen? Q0 upon reading the next one. Q0 upon reading the next one. Again, it has two options. That means it can either stay in the same state or it can switch to the state Q1. That means here in state Q0, one of the finite controls is staying in the same state Q0 and the other is going this way. That means it has switched to Q1. But say the other finite control is in state Q1, and now for the next one, that means here after reading the first one, the finite controls are split, and one of the finite controls is in state Q1 and the other finite control is in state Q0. And upon reading the next one, what will happen to this finite control? This is one of the finite control. That means again it is split into two. That means one is staying in the same state and the other is going to state Q1. And the other case you have to take. That means after reading the first one of the finite controls is in state Q1, and upon reading the next 0, what will happen? Q1 on 0, here we don't have any outgoing transition. We don't have any outgoing transitions, and in that case, here we have terminated. That means no more. That means this finite control, it is the transition for q1 on 1 is not defined. So it has ended its journey. Okay, now it is terminated. That means here upon 1 this finite control terminated. Okay, now these two finite controls are in state one of the finite controls is in state q0 and the other is in q1. And upon reading the next 0, what will happen? If q0 upon reading 0, what will happen? It is staying in the same state. That means q0. And the other finite control which is in state q1, upon reading 0, what will happen? It is switching to state q2. That means this is q2. That means here starting with the state q0, now if you have followed this path, then after reading, that means after reading 1 it has split into 2. That means for the same input symbol you have more than one outgoing transition, and suppose here for this q0 on 1 you have 2 outgoing transitions. That is why you have split this into 2. If you have 3 outgoing transitions, you have to take 3 routes. You have to take, in this case you have taken only 2 routes, and one of the route is this one, and after that again one, and in that case q1 on 1 is not defined, so that route is terminated, and the other route q0 on 1 is either staying in the same state q0 or q0 on 1 it is moving to q1, and q0 upon reading 0 it is staying in the same state, and q1 on accepting 0 it is moving to the state q2. And as you know, here your input is 0 1 1 0, and upon reading after processing this 0 1 1 0, what will happen? One of the finite control has reached q2, which is a final state. This is one of the final state. Here we have only a single final state, and we have reached the final state. And here see, the other finite control reaches q0, which is a non-final state, and this language is accepted. If this language can be accepted, if one of the routes take you to one of the final state. Here you have reached q2, and that's why this string can be accepted. This string can be accepted. That is the concept of non-deterministic finite automaton. And in a non-deterministic finite automaton is accepting the same language which is accepted by a deterministic automaton, finite automaton, and can easily convert a non-deterministic finite automaton to its equivalent deterministic finite automaton. So how that can be done, I will show you. That means here suppose that here the non-deterministic finite automaton NFA is defined like this. Q0, you have how many states? Q1 and Q2, and you have two inputs 0 and 1, 0 and 1, and q0 upon reading 0, what will happen? It is staying in the same state. q0 upon reading 1, what will happen? You can either stay in the same state or it is switching to q1. That means we have a set of q0 comma q1, and q1 on accepting 0, what is q1 on accepting 0? It is moving to the state q2, and q1 on accepting 1, q1 on accepting 1 is 5, and q2 on accepting 0 again 5, q2 on accepting 1 again 5. So this is the transition table. This is the transition table for the NFA which is given here, and this can easily be converted to its equivalent deterministic finite automaton. How that can be done? See, it is very easy. That means again starting with q0, that means Initially, suppose that m is equal to q sigma delta q0 f. This is NFSA or NFA. This is the NFA. That means M is equal to Q sigma delta Q0. Q is a set of states. Here in this case, what is Q? Q is equal to Q0, Q1, Q2. What is sigma? Sigma is 0, 1. That is the input alphabet. Here in this case, you have only zeros and ones. And transition function delta is defined by this. This is the transition function. Q0 upon reading 0 is Q0, Q0 on reading 1, Q0, Q1 and like that. And delta, what is Q0? You know that Q0 is the start state for this NFA, and F is set of final states, and in this case final state is Q2 only. Okay, M is equal to Q sigma delta Q0 F. Now I am going to have a new, that means I am going to convert this NFA to its equivalent DFA, and here this M dash is the DFA. M dash, this is the NFA, and the equivalent DFA is, here you are going to have new set of states which is represented by Q dash. Sigma, the input alphabet is same. Transition function delta dash, that means you are going to redefine delta dash. Here the new start state is Q0, or simply you can write it as Q0 dash. New start state is Q0 dash, and F dash is the set of final states. That means here this is the NFA, and that NFA is defined by like this, and I am going to create a DFA which is equivalent to this NFA, and now I am going to have the definition of the DFA, which is Q dash sigma delta dash Q0 dash and F dash. Here sigma remains the same. That means the input alphabet is same for both the NFA and DFA. Now what is Q dash? Q dash is actually, Q dash is the power set of Q. Q dash is the power set of Q means, now you have three elements in the set Q, and the power set of Q is 2 raised to Q is power set is represented by 2 raised to Q. That means it is having Q0, Q1, Q2, Q0, Q1, Q1, Q2, Q0, Q2, Q0, Q1, Q2 and 5. 5 is not defined. So we have the power set of 2 raised to Q, which is equal to the set represented by, what is this? Q0, Q1, Q2. That means 3 elements taken at a time. 3 elements taken at a time. Now you have Q0, Q1, Q1, Q2, Q0, Q2, Q0, Q1, Q2 and 5. Okay, that means the power set of Q, which is represented by Q dash is equivalent to is the set Q0, Q1, Q2, Q0, Q1, Q1, Q2, Q0, Q2, Q0, Q1, Q2 and 5. And this is the new set of states. This is the new set of states. So here we have only 3 states in this. Here you have 8 states. 2 raised to Q. Power set of Q, power set is having 2 raised to n number of elements. Here these are the new states for the DFA. And sigma is the input alphabet. Delta dash is the transition function that we are going to define here. and q0 dash new state is represented by q0 within square brackets, q0 within square brackets, and f dash is the new set of final states, and here final state means the original set the final state is q2, the original state the final state is q2, and in the set of states wherever there are q2s, that means this is having q2, this is having q2, this is having q2, and this also is having q2. Okay, now means this is a set of 4 states, that is this is 1, this is 2, this is 3, and this is 4. That means 1, 2, 3, and 4. Okay, that means this is the new, this is the DFA corresponding to the NFA. This is the NFA and the corresponding DFA is this. And say, here we are going to have 0 and 1 are the inputs. 0 and 1 are the inputs. And initially, the start state is defined by Q0. Q0. What is Q0 upon reading 0? Q0 upon reading 0, what will happen? Q0 upon reading 0 is staying in the same state Q0, and here it is Q0 itself. And Q0 upon reading 1, what will happen? This either staying in the same state Q0 or it is moving to the state Q1, and that is represented by, that means here you have a set of states Q0, Q1, and in that means that is represented by a single state and that is represented by Q0, Q1. Okay, that means here from the start state, if your input is 0, it is staying the same state, and upon reading 1, it is moving to a new state which is represented by Q0, Q1 in square brackets. That is a single state. That means this one represents the state corresponding to Q0, Q1. This is the state Q0, Q1. And see, from the start state, one of the finite control is in the same state, and one of the finite it is for after reading 1, it is moving to a new state Q0, Q1, and now you have only 2 states, and this is all the transition for this is already defined, because you have Q0 here for on 0 it is staying in the same state, and on 1 it is moving to a new state. Now you have to define the transitions for Q0, Q1. See, Q0, Q1, and this is represented this single state of the DFA. This is the single state of the DFA, and this single state of the DFA is representing multiple states of the NFA. That means Q0 and Q1. Multiple states of the NFA is defined by a single state of the DFA. Now, what will happen if Q0, Q1 on reading 0? Q0, Q1 on reading, that is delta of Q0, Q1 on reading 0, what will happen? That means the transition for Q0, Q1 upon reading 0 is the union of, or delta of Q0 upon reading 0 union delta of Q0 Q1 on reading 0. Okay, that is delta. That means the transition for Q0 Q1 upon reading 0 is, you have to verify what is Q0 on 0. What is Q0 on 0? Q0 on 0 is Q0 upon reading 0, it is Q0. That means that is Q0. And what is delta of Q1 on 0? What is delta of Q1 on 0? Q1 on 0 is Q2. Q1 on 0 is Q2. That means Q0 union Q2, and which is represented by Q0 Q2. Q0 Q2. That means Q0 Q1 upon reading 0. Q0 on 0, what is that? Q0 on 0 is Q0, and Q1 on 0 is Q2. That means taking the union of those two, we have Q0 Q2. Okay. Now, what will happen on 1? Q0 Q1 on 1. Q0 Q1 on 1 means Q0 on 1 union Q1 on 1. What is Q0 on 1? Q0 on 1 is Q0 on 1 is Q0 Q1, and what is Q1 on 1? What is Q1 on 1? Q1 on 1, Q1 on 1 is 5. That means the union of Q0 Q1 and 5, which is Q0 Q1. Q0 Q1. That means we have defined the transitions for Q0 Q1, and we have not defined the transitions for Q0 Q2. Okay. Now we are going to define the transitions for Q0 Q2. Q0 Q2. Q0 Q2 means, what is Q0 on 0? Q0 on 0, it is Q0. That means it is Q0. Q0 on 0 is Q0, and what is Q2 on 0? Q2 on 0 is 5. That means Q0 union 5 is Q0. That means Q0 Q2 upon reading 0, it is moving to the state Q0. And what about Q0 Q2 reading 1? Q0 Q2 reading 1 means Q0 on reading 1. What is Q0 on reading 1? It is Q0 Q1. See, this Q0 Q1. And what about Q2 reading 1? Q2 reading 1. Q2 reading 1, it is 5. That means Q0 Q1 union 5 is Q0 Q1. Okay. Now we have defined the transitions for this. Now, what about Q0 Q1? The transition for Q0 Q1 is already defined. What about Q0 Q2? Q0 Q1 already defined. What about Q0 Q2? The transition for Q0, transition for 0 and 1 we have defined. That means now for Q0 Q1 it is defined, for Q0 defined, and for Q0 Q1 all defined. That means, generally speaking, we have Q dash is having 2 raised to Q number of sets, but all of them are not operational. That means all of them are not reachable. We are reaching only Q0, Q1 and Q0 Q2. Okay. We are okay. Let us define, or I am going to redefine this Q0 as Q0, and this Q0 Q1 as Q1, and this Q0 Q2 as Q2, and the transition table or the transition diagram is looking like this. This is Q0, this is Q1, and this is Q2. And what are the final states? Here for this original NFA, Q2 is the final state, and wherever there are Q2s, those are the final states of this DFA. This is the equivalent DFA, and in this DFA, this is having only Q2. Here we are having only Q0. Here we are having only Q0, Q1, and here we are having Q0 and Q2. That means Q2 is part of this. So you have to make this a final state, and this is the start state. Okay. What is Q0 on accepting 0? It is staying in the same state Q0. That means 0. And Q0 upon reading 1, it is moving to a state, new state. Okay. What about Q1 on reading 0? it is moving to state Q2, and Q1 upon reading 1, it is staying the same way. That means Q0 Q1 is Q1 here. That means here upon reading 1, it is staying in the same state. And what about Q0 Q2 on accepting 0? Here, for in this state Q2, if it is accepting 0, it is moving to state Q0. That means here we have a transition, that means 0. And Q0 Q2 on accepting 1, it is moving to Q0 Q1. That means this on accepting 1 is moving to the state. That means definitely this will accept all strings which is ending with 0, it ending with 1 0. For example, suppose that I am going to verify whether this is 0 1 1 0 1 1 0 0 1. For the next one, it is staying in the same state. For the next 0, it is going to displace the state. For the next one, it is coming back. For the next one, it is taking a loop, self loop, and for the next 0, it is reaching here. That means Q2 is the final state. That means all binary strings which are ending with 1 0 is accepted by this DFA. And here I am going to redefine this. That means Q dash is the set of final states, or Q dash is the power set of Q. Q dash is the power set of Q. But in that power set you have 8 different sets. But in this case, these 3 are only reachable. That means this is not reachable. Q0 Q1 is reachable. Q1 Q2 is not reachable. Q0 Q2 is reachable. Q0 is reachable. Q1 is not reachable. Q2 is not reachable, and like that. That means these are the 3 states. And now I am going to redefine this. That means Q0 Q1. The set is defined by this is Q0 Q1. What is this? This is Q0 Q2, and this is Q0 Q2, and this is Q0, and this is Q0. So this is the new states, and Q0 is represented by Q0 in our diagram. This diagram, that is represented, and this is Q1 and this is Q2, and Q2 is the final state. And Q0 dash is simply Q0. That means this is Q0 dash. This is Q0 dash. Q0 dash represented by this, and the set of final states are here in this case only final state is Q0 Q2. Okay, in this way you can easily convert an NFA to its equivalent DFA. That means in this case, in our original transition diagram, we have 3 states. That means this is the NFA, and that NFA is represented by Q sigma delta Q0F. Q is the set of states Q0, Q1 and Q2. These are Q0, Q1 and Q2. Input alphabet is 0, 1. Final state is Q2, and the transition diagram is represented by this, and the start state is Q0 and the final state is Q2. And we are going to define an equivalent DFA equivalent to this. For that DFA M dash, we have Q dash sigma delta dash Q0 dash and F dash. That is a DFA. And for this DFA, that means we have another set of states. The input alphabet remains the same. Delta dash is the transition function, and that transition function is different. Q0 dash is also a new start state, and F dash is the new set of final states. And Q dash is having 2 raised to Q, or you have the power set of Q, that much number of elements in it. But here in this case, only 3 are reachable, so we are restricting that to 3. And the transition diagram is like this, and Q0 dash is the state Q0 in brackets, and F dash is the new states wherever there are final states of the original NFA. And this is the way you can convert an NFA to DFA. I will show you one more example. And suppose that this is show you another example. Suppose that here, suppose that you have a backward transition. Here you have a transition and that is represented by 1, and suppose that this is 0. What will happen? Initially, we are starting with the state q0 and then this is the NFA, and the equivalent DFA I am going to write. See, you have two inputs 0 and 1. What is q0 on accepting 0? Q0 on accepting 0, it is taking the same state q0, and q0 on accepting 1, what will happen? This is 1, q0 on accepting 1, it is either staying in the same state or it is switching to state q1, and that is represented by q0, q1. Now, the transition for this is already defined, and this is the next state you have created, and the transition for that I am going to define. That means q0, q1. q0, q1 on accepting 0, what will happen? q0 on accepting 0 is taking the same state q0, and q1 on accepting 0, it is moving to q2. That means q0, q2. And q0, q1 on accepting 1. q0, q1 on accepting 1 means q0 accepting 1, it is taking the same state or switching to q1. That means q0, q1. And what is q1 accepting 1? q1 accepting 1, that is not defined, so it is 5 and it is staying the same state. Now, the transition for this is not defined, q0, q2. This is q0, q2 upon reading 0. What will happen? q0, q2 upon reading 0. q0 on 0, it is q0. And q2 upon reading 0. q2 upon reading 0, it is staying in the same state q2. That means q0, q2. And q0, q2 on 1. q0, q2 on 1, what will happen? q0 on 1, it is either state q0 or q1. That means q0, q1, and q2 upon reading 1. q2 upon reading 1, it is coming back to q1. That means q1 union q1 means this q0, q1. Okay. Now, the transition for q0, q2 is over. q0, q1 already defined. q0, q2 already defined. q0, q1 already defined. That means we have three states. I am going to redefine this as q1, q2 and q3, and here the final state is q2. That means here we don't have any q2s here, this is having q2, so make this the final state. That means q3 is the new final state, and you have q0, q1, q2, and this is q0. q0 upon reading 0, it is staying in the same state q0. q0 upon, this is q0, and this is q1, and this is q2. q0, q1, q2. q0 upon reading 0, it is staying in the same state. q0 on reading 1 is moving to q0, q1, which is represented by q1. That means here upon reading 1, this. Now q1 accepting 0 is moving to q0, q2. q0, q2 is q2. That means q1 accepting 0, this is, and q1 accepting 1 is q0 q1. That means it is staying in the same state. That means on reading 1 is like this, and q2 upon reading 0. q2 upon reading 0, what will happen? It is staying in the same state. That means q2 upon reading 0, it is staying in the same state, and q2 upon reading 1, it is moving to q1. That means this is 1. Okay, so this is the way we can convert. That means here q2 is the new final state, and if you have a finite automaton or if you have a non-deterministic finite automaton, you can easily convert that to a deterministic finite automaton, and there is a proof for this. That means with keep this in your mind, and uh, we are going to have a theorem for this, and that we are going to prove. That means if you have a non-deterministic finite automaton, you can find out, or you can have an equivalent deterministic finite automaton for that, and that we are going to define. Okay, thank you.